Hello. Today we're going to be looking at a question on a table in stable equilibrium. It's a support question and it uses equal and opposite moments. Okay, we'll start by reading the question. So the following diagram shows a side view of an uneven table in stable equilibrium. The table is modeled as a uniform rigid rod of mass 70 kilograms. The legs of the table are modeled as two pivots. A block of mass 10 kilograms is placed such that its center of mass lies 1 meter away from the right-hand side of the table. The question asks us to calculate the value of the reaction forces at both pivots A and B. So that's going to be here and here. First thing we're going to look at is just the wording in the question, right? We are going to look at the words stable and equilibrium. I'm also going to look at the word uniform here as well. So we'll start by looking at the word stable, okay? Word stable implies that there's no net moment, okay? So no net moment, which means that the total anti-clockwise moment, okay? So that would be this one here, is equal to the total clockwise moment, which is this one here, okay? It's a complete balancing. Think about a seesaw if you're both on each end. Second word is equilibrium, okay? Equilibrium means the forces in the upwards and the downwards direction, and also in the left and the right, but we're not going to be looking at horizontal forces in this question, are completely balanced, okay? So up equals down. There's a complete balance of these forces. The word uniform here, this just means its center of mass lies at its midpoint, okay? So center of mass lies at its midpoint, at least for a one-dimensional object, okay? We're looking at a side view here. This is exactly the case. So now, let's start by labeling on the forces that we know exist. So the forces at play here are obviously the reaction force at A and the reaction force at B. So we'll label these RA and RB. RA and RB. We're going to think about the other forces that we can label on this diagram as well. Well, one of them is going to be the weight of the rod. Okay, so that's going to be 70 kilograms times, if you remember, weight, F equals mg, where g is 9.81 newtons per kilogram. So the weight is going to be 70 times g, okay? Similarly for this block here, this is a 10 kilogram block acting from its center of mass downwards. It's going to have a shorter arrow actually because it's only got 10 kilograms. So we can make this one a little bit longer for scale. This one is going to have 10 g of force. Again, it's not to scale, so we don't have to care too much about the size of the arrows. So now we have enough information to start writing out our moments, okay? So the trick here is because we have two unknowns, we can pivot around either one of these pivots, okay? So if we choose A to be what we pivot around, so pivot at A, the trick here is that RA has absolutely no contribution to the moment if we use this pivot because its distance from the pivot is 0, okay? So it's actually only going to be this one, and this one, which are going to have contributions. So we should be left with an equation with one unknown, which is RB. So we should be able to get it. So let's have a look and see if we can. So pivoting at RA, let's take clockwise moments to be positive, okay? So anything pulling down and clockwise, as we can see with the weight here, that's going to be positive. Anything pushing up and anti-clockwise is going to be a negative moment, okay? So we can equate the positive, or the clockwise, and the negative anti-clockwise moments, okay? And that's easy to see just from the diagram. Just think about pushing through that pivot. You'll instantly see which direction it's going to be. So pivot A, okay? So we'll take 70g, so that's the size of our first force, the weight of the table, multiplied by the distance from the pivot. So we know the distance to the middle is going to be 2.5 meters. So that's the center of mass of the rod. From pivot A, that's going to be minus that initial 1 meter as well. So it's 1.5 meters, okay? So we add on the weight of the block, adding into its own moment. So what's the moment caused by the weight of the block? Well, that's going to be obviously the weight of the block first, multiplied by its distance from our pivot. So it's 1 meter in from the right-hand side, but our pivot is also 1 meter in from the left-hand side. So it looks like it's going to be 5 minus 1 minus 1. So that's going to be 3. And this is going to be equal and opposite to our reaction at B, multiplied by the distance away from pivot A. So it's already in 0.5 meters from the right-hand side, and pivot A is in 1 meter from the left-hand side. So we're 1.5 meters out, effectively, out of the 5. So RB times, so 0.5 plus 1 is 1.5. Take that away from 5 is 3.5 meters. Okay. Easy rearrangement here. All we have to do is divide by the 3.5 and bring that on the bottom, okay, and turn that into a fraction. We find that RB is equal to, and we can put our 9.81 in now for G, is 70 times 9.81. So it's reading off here. So 70 times 9.81 times 1.5 plus 10 times 9.81 times 3, all over 3.5. So we'll divide all that by 3.5. And this is equal to 378.39 newtons. So now, we reach a bit of a crossroads here. We could find RA using a pivot at B, okay? At B. If you remember what I said earlier, you might have noticed that from equilibrium, we can also look at the raw forces acting. Since we now know what RB is equal to, and we know that these two should be equal and opposite to these two, well, these two, so RB plus RA, we should be able to figure out RA straight up, okay? So we'll try this at the bottom just to see if they match. So RA plus RB should be equal and opposite to 70G plus 10G. Let's have a look and see if they work. So rearranging this, we just take away RB from the left-hand side. We get RA equals 80G, so that's our summation here, 80G minus RB, which equals 80 times 9.81, substituting in for G, minus RB, which we just calculated. That's 378.39. So we'll pop that in. 378.39. And this comes out to 406.41 newtons. Okay, so let's see if that matches up with our other result. So let's try pivoting at B now. So here we go. Once again, the trick stands. RB acts exactly on pivot B, so its distance is 0, so the moment that it causes is 0. Let's take a look at the directions that we're going to want to have these forces acting on. So let's think about, firstly, the weight. Okay, so the weight's going to pull it around this pivot downwards, so that's going to go down like this. So this is anti-clockwise. So this is our negative direction. So we'll want this to be on the right-hand side. Okay, so think about the left-hand side. This is going to be this one here, RA, which goes around like that. So that's clockwise. So we'll start with RA. Okay, so RA on our left-hand side. It doesn't actually matter which side, obviously, you do the moments on, but it's good to keep it in practice, just in case the question does get a little bit more complicated. So you have RA times its distance from RB, which, as we calculated already, was actually 3.5. So 0.5 in, you're 1 meter in, so that's 1.5 in from the total 5 meters. So that is 3.5 meters. Okay, don't need the meters. Equals. So now we can do equal and opposite moments. So we'll start with the 10 kilogram block. Well, that's 1 meter in from the right, but RB is already 0.5 meters in from the right. So 10G times 0.5. So it's just that extra 0.5 meters past the pivot here. Okay. Plus 70G. So here's our 70G here. And what's our distance away from the pivot? Well, it's 2.5 meters away from the right-hand side, okay? but pivot B is already 0.5 meters in from the right-hand side. So it's actually 2 meters away from RB, so 2 meters away from the pivot, times 2. So therefore, rearranging for RA, the reaction at A, that's going to be all of this stuff divided by 3.5. Okay, so we're just bringing that 3.5 over and under effectively. So let's pop in our values for G. So that's 10 times 9.81 times 0.5 plus 70 times 9.81 times 2, all over 3.5. All over 3.5. And that is equal to, let's take a look, 406.41 newtons. Exactly the same result as we got from the equilibrium approach, which shouldn't surprise you, or maybe shouldn't surprise some of you, but it's good to see that both of the methods do match up and give the same result.